Okay, so today we are going to talk about the least squares regression line, or the line of regression. We're going to refer to it as the LSRL, and we're going to learn a couple of formulas that will help us find that LSRL. First, we need a formula for slope, and the formula for slope is B is equal to R times S sub y over S sub x. That's the correlation coefficient times the standard deviation of y over the standard deviation of x. We also need the formula for the y-intercept, and that will be A is equal to the mean of y minus B times the mean of x. To work with these two formulas in order to get the LSRL, we're going to start with an example. And in this example, we have the percent increase in advertising versus the percent increase in sales. The first step is always, always, always to define your variables. So x, oops, not x bar, just x. X is going to be the percent increase in advertising. And y will be the percent increase in sales. Now, we happen to know some information about the percent increase in advertising and the percent increase in sales. And these are the facts that we know. We know that R, or the correlation coefficient, is 0.9171. We know that the mean of x is equal to 14.7. So the mean percent increase in advertising is 14.7 with a standard deviation of 6.4987. We know that the mean percent increase in sales is 9, and the standard deviation of the percent increase in sales is 3.298. Okay, so we are going to go ahead and apply these particular formulas and figure out what we have here. So if we want to calculate the slope, we're going to start with B, and we know that B is R times the standard deviation of y over the standard deviation of x. And so we're just going to plug things in. 0.9171 times 6.4987 divided by 3.2998. And we work that out. That should come out to be 0.4657. We can also calculate A, which is y, the mean of y, minus the slope times the mean of x. So the very same slope that we just figured out, we're going to use again. So the mean of y is 9 minus 0.4657 times 14.7. That gives us a y-intercept, or an A, value of 2.1542. Double check. Those two values are going to allow us to have our LSRL, or our least squares regression line. We never, ever, ever refer to our equation in terms of y, but y hat. That little hat, which should remind, it's a carrot really, but it should remind you of that birthday hat and from when you were a little kid. And that tells us that this is a line that's making predictions. It is not actual fact. These are not observed values. 2.1542 plus 0.4657x. And there is our LSRL. So this gives us some information that we can now use. If we want to interpret the LSRL, we need to know a few things. We need to know about the slope, we need to know about the y-intercept, and we need to know a little bit about the correlation and the coefficient of determination. Let's start with the slope. Oops. Slope. We know that our slope came out to be 0.4657. And what this really says is there is an increase of 0.4657% in sales for every percent increase in advertising. So essentially, we are just taking the slope or the rate of change and putting it in context. That's really important in stats. We've got to be able to put things in context. We also have our y-intercept. And so our y-intercept lets us know a little bit about what's happening at the y-intercept. So when we had our y-intercept, and the last slide, y-intercept was A, right? And A was equal to 2.542. And that tells us kind of our starting point. So when there is a 0% increase in advertising, there will be a 2.1542% increase in sales. And so we're really just talking about slope and y-intercept and putting them into context. And if we continue, we also really need to be able to talk about our correlation coefficient. Recall that a correlation coefficient is R. So R for this particular problem was 0.9171. And so when we talk about interpreting this problem, we want to talk about the form, the direction, and the strength. And that's where R comes in, because it does a lot of that for us. The correlation coefficient is only for linear models, so we're good with that. Direction, we know that our correlation coefficient is positive, so we know that. And we know that 0.9171 is fairly strong. So this is how we would say it. We're going to go ahead and put it in context. There is a strong, positive, linear association between the percent increase in advertising and the percent increase in sales. And finally, there is something that is related to the correlation coefficient, and that is the coefficient of determination. Now, the correlation coefficient is R, but the coefficient of determination is R squared. Literally, the correlation coefficient squared. Okay, and if we know our correlation coefficient, we can find our coefficient of determination. So if R equals 0.9171, then R squared is going to be really easy to find, right? We're just going to use our calculator and we're going to square it. And we're going to find that R squared is equal to 0.8411, rounding to the 4 decimal places. Now, why is the coefficient of determination important? The coefficient of determination is important because this helps us to know how much of the variation in our variable, in our y variable, can be explained by the LSRL we just found. So in this case, 84.11% of the variation of the percent increase in sales can be explained by the LSRL of percent increase in sales increase in sales on the percent increase in advertising. Okay, so we're going to wrap this up here, but in class we're going to talk about what all of these things mean with other examples. Have a good evening.